Hello. So continuing this contest, 12th bi-weekly contest of Leetcode. The last problem is palindrome removal. And so the problem says, given an array, in one move you can select a palindromic subarray. So from position I to position j, such that I is smaller than j, and you could remove that subarray from the given array. And note that after removing a subarray, the elements on the left and on the right of the subarray move to fill the gap that is left by removing this subarray. And the goal of the function is to return the minimum number of moves that we need to remove all numbers from the array. So with an example here, let's say this array 1, 2. Any single number is a palindrome, right? And so here the only palindromes we have are single numbers. So we can remove 1 first, that's 1 move, and then remove 2, that's 2 moves. With this example, the optimal way to get the minimum number of moves is to removing first 4, and then after that we will end up with 1, 3, 1, 5, and so 1, 3, 1 is a palindrome, right? And so we can remove, because basically this equal to this, and the middle can be whatever. This is just a normal palindrome, the same way with letters, right? And after that we remove this portion, and then there is only 5 left, so we remove that. So we did 3 steps, removed 4 first, and then 1, 3, 1, and then 5. So that's the problem. Now how can we solve it? So you can see the problem says we want to return the minimum number of moves needed to remove all numbers from the array. Whenever we see something like this, minimum number of moves, we need to directly think about using dynamic programming, right? And so let's see how can we solve this problem using dynamic programming. Okay, so let's see how can we solve this using dynamic programming. So one useful thing to always do using dynamic programming is to answer a couple of questions, to think about a couple of things. So first thing we should think about is, what is our DP state? And what is the actually first let's just think about the goal of the problem, and then think about our DP state, and think about some base cases, and then think about the transitions that we will do. Like, how can we from a problem decompose it into a set of sub-problems, and then accumulate that to get another solution, right? So what is the goal? So the problem literally just says we want to return the minimum number of moves needed to remove all numbers in the array, right? So usually the state should be something similar to that, right? So here what we can do, our state is min number of moves to remove all numbers in subarray I to j. So why I to j, right? So usually dynamic programming problems are either work on a prefix or a suffix of something, or on a substring or a subportion. Here, since the problem says we can remove from any place in the array, and we can remove one element, or if the palindrome is bigger than one element, we can remove even a middle portion, right? So we can have something like this, a set of numbers, and the palindrome maybe is in the middle, and we can remove that, right? Or maybe the palindrome could be here, and it could be multiple, and we can remove that, or here and multiple, and we can remove that. So it's not always prefix, it's not always suffix, and it can be in the middle. So this directly says to us that it should be something similar to a substring, right, or an interval. And that's why the DP state is in a subarray from I to j. Now let's see what are the base cases. So a couple of things stand out here, right? Because DP for I to I, right? minimum number of moves to remove all numbers from, let's say, position 1 to position 1. that's just removing one element, and since one element is a palindrome, we can just remove it in one move, right? And the other thing is, if you have two numbers, let's say 1, 2, right? These you can remove, you have to remove in two moves, right? Because you can remove this one and then this one. Each is a palindrome. But if you had something like 1, 1, you can remove them in one move, because a palindrome, as the problem says, can be removed in one move, right? And so dp of I to I plus 1, if you have two elements, depends on whether they are equal or not, right? So if they are equal, then so it would be equal to 1 if array of I, let me just give myself space here, is equal to array at I plus 1. Otherwise, it's just 2, right? Because both are palindromes, so it's just 2. Now, what are the transitions? So if we know the state for something, how can we deduce dp of I to j? So one thing that usually helps with transitions is to just think about all the choices that we have at any point in our state. And so here, well, the choices in some way can be either one letter or two letters, and in that case we can use this base cases formula, right? Or the other option is that we have, let's say, a palindrome like this. So we could either, let's say we have an element so we may have A and A here, right? So in that case, what we can do, so these are the cases. So in this case, what we can do is that, or we can have something like this, right? We can have, I'm just saying A and A to see, so that you can see that, or maybe let me just use numbers so that I don't confuse you. So here maybe it's 1 and 1, or maybe it's we have 1 and let's say 4 here, right? So we don't care about the middle for now. We are just looking at the different choices we have at any random point, and maybe there are some other stuff here, or maybe there is nothing. We don't care. We want to find some kind of a general solution. So this is I, and this is J, and this is I, and this is J, right? So at this point, for the first case, that means that our dp of ij is going to be equal to dp of maybe let's just, yeah, dp of I. So this is I plus 1, and this is j minus 1. So dp of I plus 1 and g minus 1, that's whatever is the solution for this one, plus 0 if both are equal, if array I is equal to array j, which is the case here, right? The 1 and 1. Or if they are different, then in that case it's 2, because we need to remove this one and this one separately, right? But if they are equal, then at that point it just depends on what's in the middle. If it's, because why is it plus 0 and not plus 1? Because if it's 3, then we can remove this in one move, because the entire thing is a palindrome. If it's something like 1, 2, 3, 1, then we can remove this one with one move, right? And then we can remove after that we have 1, 3, 1, and we can remove that entire thing in one move, and so we end up with 2. And 2 is actually the dp for 2, 3, right? 2, 3 can be removed with one move and one move, so that's 2. So you can see it's 2 plus 0, it's not 2 plus 1, so that's why we have this 0 here. Okay, so we know this case for, it can be either moving that or moving that, but maybe it can, an optimal solution is in a different. So maybe the optimal solution would be something like this. Let's say maybe we have 1 here, right? And then we have a palindrome in this portion, right? Let's say we have 1, 3, 1. or maybe 2, 3, 2, right? So here, this is a palindrome, it can be removed in one move, and this is a palindrome, it can be removed in one move. So here, the optimal solution is actually 2. So if we use this method here and take 2, then we would have 1, 1, and then 2 for this, so we'd have 4. So that's not the optimal solution, right? And so instead, we should also take as a min, as another choice here. So this would be min of that, of 1 here, and of this thing, which is basically, so this is I, we have something here, and we have something here, and this is j. So it would be I plus 1, so that we can get this portion up until j, plus 1 for removing this one here alone, right? Well, this thing can happen also on the other side, right? So we could have something like this, where we have 2, 3, 2, and 1, right? In that case, the optimal solution here is to remove this portion first, and then remove this one alone. And that will get us 2 moves, right? And so in that case, it would be something like this. So let's call this one, this portion here 2. So that would mean we need to do min of 1, of 2, and then of dp of I. So this one is I, and this one is j. So it's I until j minus 1 here. And then plus 1 for removing the element at position j. So far we listed 4 choices, right? And we have them in our, we will do the minimum on all of these choices. Another last choice that is definitely possible is that we might have something like this, where actually a palindrome is like in the middle. So maybe it's something like this, 3, 2, and then 6, 7, 6, right? So here the right thing to do is to the optimal solution is to remove this portion here in one move, right? And this portion here is in one move, right? And basically just remove at this position, right? The other possibility is that we might have something like this, where we have 4, and then we have 6, 7, 6, 2, 3, 2. So the right solution there, the optimal solution, is to remove this, and then this, and then this, in basically 3 steps. So you can see the middle can be anywhere, and then we need to get the minimum, try all of them and get the minimum, right? That's what dynamic programming does. And so to achieve that, what we are going to do is we are going to go try all the different positions for the middle. So that would mean any position between I and j. So for k in range I to j, right, we will say dp of ij is going to be, of course, the minimum of all the things that we calculated so far, which are 1 and 2 here, and 3. Let's call this one 3. With this new thing, which would be, so we will be taking the middle k. So it's whatever dp for the left side plus whatever is for the right side. So in this case here, the right side would be this portion, the left side would be this portion. And the left side, if this is k, it would be just dp of I to k plus dp of k plus 1 to j. So remember, this is inclusive, so from I to k inclusive, right? So this is k, and so it's this portion, and this is the other portion. And so now we took all the possible choices and we take just the minimum, right? And since we are doing this, since we are doing all the enumeration of all choices, we must find the minimum, right? So the last thing that some DP problems have and you need to think about is what is the order of iteration. So here you could see the way that I thought about the problem and divided it here is that I first look for the edges and find out what I need and then go to the middle. So you can see that what I want is for the left to start out from the end. So, and then basically I want to start out with like this. So I want to start out with just this portion first, right? And then calculate the solution for this, and then the solution for this, until I calculate for the entire array, right? And so to do that, we can just do the loop for I from the last position, right, which is n minus 1, and go down, right, so that we can try I to be here and then try I to be here. And so that would be going down until 0. In Python it's like this. And then for my right position, right, so when I pick first I here, I need to pick j here. When I pick I to be at this position, my j needs to be first here, and then I need to try it also here. And then after that, when I move my I position here, I need to try j here and then try it here. Since it's an interval, I need to try all the possible intervals, right, and then try it here. So that would mean my j needs to be from I, right, to get one element, and then all the way until the end, right, so that I can do this order that I said here, right? So that when I'm at the full solution here, to be able to use dpi plus 1j and ij minus 1, I want to have the rest already computed. And so that's why I'm starting from a single element at the end and then going left until I have the entire array, right? And so now that we know the general thing that we want to implement, and we know the base cases here, or at least we know the simple cases in our loop, we know how our loop will be structured, and we know the transitions that we need to do. Let's do it in an organized way on Leetcode and see if the solution passes. Okay, so now let's implement the solution that we just discussed. So first, I'm just going to put in the length here, and then I'm going to initialize my dp array, right? And so that dp we can just use either the max, like inf here, infinity, but we also know that the minimum number of moves at most is going to be removing each element one at a time, because each element is a palindrome, and so at most is going to be n. And so let's just put n by default, right? And so I was just going to initialize the table here. So this is for in range of n. And something that I would return here is, what do we need to return at the end? We need to return for the entire array, right? The minimum number of moves for the entire array, right? So that's n minus 1. And now we need to do our loop that we just said in the order that we said, which is first going from minus 1 all the way until I reaches 0, which is the start of the array, which is the last one, the result that we want, right? So by minus 1 each time. And then the j, we said that it starts from I and ends at n, right? So that we can first calculate just for the last element, and then for the 2 last element, and then for the 3 last elements, and then all the way until for the entire array, right? And so let's do our base cases that we discussed. The first base case is when both are at the same position, and in that case our dp at I and j is just 1, right? Because that's a palindrome, right? One element is a palindrome. The second used case, or the second base case, was that when for 2 elements, right? So when I is equal to j plus 1, in that case it's either so it depends on if the array at I and j are equal, right? So if they are equal, then we have a palindrome, so it's like something like 1 1, and we have just with one move we can eliminate it. Or it's 1 2, and in that case it's with 2 moves that we can eliminate it, right? So if it's this, then it's 1, otherwise it's 0. And then sorry, otherwise it's 2 actually, because it's for 1 and 2, right? So these need 2 moves. Yeah. Now we are going to just plug in all the use cases that we just enumerated in the explanation. So let's just enumerate them and take the minimum. So the first one was taking the middle portion and just eliminating the 2 elements at the endpoints. And that is, we add 0 if they are equal, right? Because then whatever, as we explained, whatever in the middle is the number of moves we need. Otherwise it's 2 because they are different and we need to remove each one of them separately. Or for example, it's the entire right portion that is a palindrome, and only the first element at position I needs to be removed so that the rest becomes a palindrome. In that case, we need to have I plus 1 and J, and then one move for removing the first element at position I. Or it's the same thing, but it's the last element that we need to remove so that the left portion is the palindrome. So that's maybe the case. So we are just enumerating all possibilities. And the last possibility is that, let's do it separately, is that it's like, for example, something like this, where we have x, 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 and then y, y, y. And so this is a palindrome and can be removed in 1 move, and this is a palindrome and can be removed in 1 move. And in that, so this case here is the case where it's x and then y, y. So this one can be removed in 1 move since it's a palindrome, and the x needs to be removed alone. This case here, it's x, 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 and y. So this portion is a palindrome and can be removed in maybe 1 move or multiple. This is just to make it clear for you, like in the case of just 2. And this one is the last element. In this case, so it can be either, like, let's say the extreme case where they are all the same character. Then this one can be removed in 1 move and this one in 1 move. It doesn't make sense to do any of these cases, right? So that you could just say 2 moves, because this is a palindrome and this is palindrome, right? And so to do that, let me just mention what is this case. So this case can be either x, and then you could have y, 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 and then x. In that case, it's just 2. It's just 1 actually, because this entire thing is a palindrome. And so you need to just say this portion here can be removed, this portion up until the last x can be removed in 1 move, and then this entire thing is in 1 move. In that case, this is the case where we are adding 0. The other case where we're adding 2 is the case where we have, let's say, x and then y, 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 and then z, right? So you need to remove this one separately, this one separately, so that you can get this middle thing as a palindrome. So that's why we do plus 2, right? Now for this case here, let's try all of them and see. So we try all of them and see if there is a one that gives us a better solution. And so to do that, we just try all of them, and our dp of I j is equal to the min of dp of ij, which is whatever result we had before, and of the trying if all the left portion plus the right portion would give us a better solution, right? So basically that means that you have something like this, where this is I, and this position is j, and then this position is k, and then this position is k plus 1, and this position here is j, right? So see how many moves can remove this portion and how many moves can remove this portion, and the entire thing can be removed in both, the sum of both, right? So that's what we are doing here. And then at the end we just return the result that we want. So let's run this and submit. Okay, so there is one error here. Let's see, what did I do wrong? I plus 1 equal to j, that's the same thing, but equal to 1. They are equal, otherwise it's 2, that's correct. So this one is I plus 1, j minus 1, and 0 if they are equal, otherwise it's 2, that's correct. I plus 1, j plus 1, yep. I j minus 1 plus 1, and then this one plus 1 j. That also looks good. Okay, so I think it's just parentheses missing here. So let's just add them. Okay, so we got time limited exception in one of the last cases here. So sometimes in Python, doing it with a for loop, because you will be doing a min on every iteration, may make it slower. So I'm just going to do it with a list comprehension here. So instead of doing it like that, I'm going to calculate the min for that entire portion, right? And use the list comprehension to pass the parameter k. And let's see. So the min of that, and then one other parenthesis. Okay, let's submit. Okay, so that passes. So yeah, just to say here, so we followed the template of asking the DP state, the base cases, the goal that we want to return, and then listed all the choices for the transitions, and then thought about the order of iteration that we need to do so that when we are at a state, we are sure that we already have computed all the subproblems. And then at the end, we just put that together, and that's pretty much it. Yeah, so that's it for this solution. Thanks for watching, and see you next time.